Before proceeding further with the discussion of the relation between the electric field and the magnetic field, I would like to go back just a little bit and talk about the Lagrangian. In relativistic mechanics, we were analyzing the problem of a particle in an electromagnetic field. And we said at the very beginning that in order to analyze the problem, we would consider a particle with a velocity which is small compared with the speed of light, because we started from this expression from the kinetic energy and from the Lagrangian, and then we derived this expression. I would like to highlight the fact that this expression of the Lagrangian here is written in invariant form. So what does that mean? It means that we can choose any arbitrary frame of reference. In particular, now we are considering inertial frames. When we consider inertial frames, we are considering Lorentz transformations. So the metric of the problem is this one right here, era mu nu. This expression right here, since this is an invariant of the theory, this doesn't change. If we multiply the Lagrangian by some constants, or if we subtract and add some constants like this one here, we would obtain the same equations. So I would like to point out the fact that this is very general even if the particles were moving with very high velocities. I mentioned that when we are considering velocities that are small compared with the speed of light, this d tau right here, proper time becomes approximately equal to time in the particular frame of reference that we are considering. This is an invariant quantity, d tau, whereas dt depends on the frame of reference that you choose. So if v is much smaller than the speed of light, this becomes approximately equal to 1, and then d tau becomes approximately equal to dt. But this expression is very general. If by these dots here we mean that we take the derivatives with respect to proper time, then this expression still remains true in reference frames in which the particle is moving with very high velocity. And I would like to show you another derivation for the Lagrangian here, how to derive this Lagrangian directly without considering the kinetic energy in classical form, just like this, and then deriving this expression. We can also derive it directly from considerations that we did use in special relativity. So in special relativity we saw that if we have just one particle in four-dimensional spacetime, we define the action and then we define the Lagrangian to be minus m0, the mass of the particle, times c squared, and then we put ds right here. So this is the action that we minimized in order to find the equations of motion of a particle that is not staying in an electromagnetic field. So the particle is just moving in space-time. So it's just a free particle. But in this case we also have an electromagnetic field. So we need to consider something additional to this thing right here. And I would like to point out that this ds here is just c times d tau. And this becomes equal to c square root of 1 minus v squared over c squared dt. The first equality here is very general, it holds true in every reference frame. The second equality implies that we are considering just one inertial frame. So in particular this velocity here is the velocity of the frame of reference that we are considering, which can be equal to that of the particle. In special relativity sometimes we can use a frame of reference that is at rest with respect to the particle, and then another frame of reference that is moving with some kind of velocity v with respect to the particle. So if we are looking at the particle from that particular frame of reference, we see that the particle has a velocity equal to v. So sometimes when I say velocity of the frame of reference, we can also think of the velocity of the particle to be that of the frame of reference, but we are choosing different ways of looking at the problem. Anyway, if I substitute this expression there, and actually I don't need this square sign here, sorry, this square sign is wrong. I just need minus m0 c times ds. In the action that we defined in special relativity, there is no square here in the speed of light, because if I substitute this expression, then I get the c squared, so that's the correct one. So I get equal to integral minus m0 c squared, and then we get 1 minus v squared over c squared, and then I have dt. Or this thing here is just d tau. I can use either d tau or dt. It depends on how I would like to express my equations. So I will use d tau, and if I use d tau, the action of just the free particle is equal to the integral of minus m0 c squared, and then I have d tau. But if I have an electromagnetic field, I need to add some terms, one invariant quantity, and the invariant quantity that we need is just this one right here. And this is just the way to introduce an invariant quantity related to the electromagnetic field that we represent by this 4-vector a mu. So I can rewrite the action by adding another action of the interaction between the particle and the field. So here I will just add minus q a mu x dot mu over c times d tau. So in this case I will write d tau, not just dt, because I'm considering the possibility that the velocity of the particle is not small compared with the speed of light, so d tau is not approximately equal to dt. Now I would like to show you that this action will give us something very similar to this expression. So I have minus m0 c squared minus q a mu x dot mu over c d tau. Or if I want, I can also rewrite this like this. So I can rewrite it as integral of minus 1/2 m0 c squared, and then I have minus 1/2 m0 c squared minus q a mu x dot mu over c, and then I have d tau, which I will put here because I have just run out of space. So this is the integral d tau, and then I have the parentheses. Let me show you something. So I have minus 1/2 m0 c squared, and then these two terms here multiply d tau. So let me consider this term right here. So if I consider this term with this d tau, I could rewrite it in a different way. The ds element, which is equal to c d tau, I can rewrite this as dx mu era mu nu times dx nu. This was the expression for the invariant quantity written in special relativity. In general relativity I just replace era mu nu by g mu nu, and I can also divide this expression by d tau here, and then multiply by d tau squared, of course. Dx mu over d tau I can rewrite as x dot mu. So this dot here in this case represents the derivative with respect to proper time, and this is x dot nu. This is not c d tau. This expression here is not ds, but it is ds squared. So we get a square here, actually here and here. From here I get that minus 1/2 m0, and then we have c squared d tau. I can rewrite it as c squared d tau squared divided by d tau, just like this, right? So instead of c squared d tau squared, I can rewrite this expression here. So I get minus 1/2 m0, and then I have x dot mu era mu nu x dot nu times d tau squared divided by d tau gives us d tau. Era mu nu times x dot nu can also be rewritten as x dot with a lower index, so I can rewrite it like this, times d tau. So if I rewrite one of these two terms right here multiplied by d tau, which is this term here, like this, I can rewrite the action in this form. So this is equal to integral d tau minus 1/2 m0 c squared, and then I have minus 1/2 m0 x dot mu, and then I have minus q a mu x dot mu over c. Take a look at this expression right here. They are pretty much the same quantities as you can see, but here's a minus sign, here's a plus sign in this first term. That doesn't really matter, because remember, this is just a constant. These two are constants when we express everything in terms of d tau. So what does this mean? It means that the equations of motion remain the same. So even for a relativistic particle, a particle that is moving with a very general velocity, we would get the same equations of motion that we derived by considering the classical case. So this is the power of tensors, because in general they will allow us to keep our equations in the same form. Next time we will continue from here, so we will try to find the relations between these fields, electric and magnetic fields. So in this case, as you can see, they are expressed in terms of the vector potential and this A0 component. But in Maxwell's equations, you don't see this A field and this A0 scalar. You just see the relations between E and B. So this is what we are going to do.